Good afternoon. Let's use this problem 3-43 and 3-44 from Hibbeler's Statics and Mechanics of Materials 5th edition. Let's solve it both manually and then we'll check our solution using the CAD system. We use SolidWorks in this case. So it says determine the magnitude of the moment of the force about the X, Y, and Z axes. Solve the problem using the Cartesian vector approach and the scalar approach. So the Cartesian vector approach, right here, we want to say that the magnitude of the moment about the origin is the position vector from A down to B, that position vector, cross product with the force vector, and the force vector is a Cartesian force vector, is given here as 4I 12J minus 3K pounds. The square root of the sum of the squares of those is 13 pounds. So that would be the magnitude, and that's its Cartesian force vector. So the position vector from A to B would be 4 in the X, a positive 3 in the Y, and then a minus 2 in the Z-axis. We cross product that with the force vector, and we can write that as a matrix. And we write our I, J, and K out here. J is always started with a negative. I cross product is 3 times a minus 3 minus a minus 2 times 12. That gives us 15 I. J is 4 times a minus 3 minus a minus 2 times 4, all in a negative, and that gives us 4J. And K, if we cross product K, that's 4 times 12 minus 3 times 4, and that gives us a positive 36K. So the magnitude of the moment about the origin due to this force is 15I, 4J, and 36K. The square root of the sum of the squares of those is 39.2 pound-feet. And if we check our answer so we can maybe have a greater appreciation for what the cross product does, we can use the force times the perpendicular distance. That's a concept that's easy to visualize, easy to understand in 2 dimensions, a little bit more difficult in 3 dimensions. So if we use the CAD system and create the same geometry as a 3D model, we can ask the system, what's the distance? If we query this, come up here with measure, the distance from the origin down here to this force vector, and there's the normal distance, 3.0157 feet. So that distance times 13 pounds, 3.01547 times 13 pounds, so the force times the perpendicular distance line of action is also 39.2. So we get the same answer there, whether we're using the manual method of cross products or using the CAD system of force times the perpendicular distance to the line of action, get 39.2 pound-feet. And then if we use this scalar approach, that's a little bit more intuitive in the respect that we're taking the force times the perpendicular distance. If we look about the x-axis here, here's the x-axis, and we break this into the 4 in the x, a 12 in the y, and a minus 3 in the j. Any moment about, any force about the x-axis, or any moment about the x-axis, would not be created by a force that's parallel to the x-axis. So it's only the 3, and you can see that it's a negative because it would be rotating clockwise. So a minus 3 times 3, and then the 12 would be positive 12, and its perpendicular distance is 2. So positive 12 times 2. So that's a minus 9 plus 24 is 15, and that's exactly what we get up here, is the 15 in the x-axis. About the y-axis, anything parallel to the y, the 12 wouldn't cause any rotation or moment, but the 3 would. The 3 times 4 is a positive, but the 4 would be a negative one. Minus 4 times the perpendicular distance is 2, or 4 times 2. And the difference between those, minus 8 and 12, is a positive 4. That's what we got here using the cross product, is positive 4 about the y. And about the z-axis, so positive z is up here. The 12, or the minus 3 wouldn't cause any moment about it because it's parallel to it, but the 4 would. It'd be causing a negative rotation. Minus 4 times this perpendicular distance is 3. And then the 12 would cause a positive rotation about the z-axis. 12 times the distance to that axis is 4, so 12 times 4. And that, of course, gives us the difference between a minus 12 and a positive 48 is 36 pound-feet. And that's, of course, what we got here about the z-axis. So this is the scalar notation method. This is the Cartesian vector method. And then, of course, I checked it with the SolidWorks method of just the force times the perpendicular distance. And the square root of the sum of the squares of those, of course, would be 39.2. So 34 says, what's the moment of the force, this force, about the AC axis? How much of a moment would be created by this force at B? How much moment would be created about this axis AC? Well, the manual method is to use the dot product. We get the unit vector of that axis AC, dot product with our moment vector, and that unit vector is 4, or the position vector from A to C is 4i and 3j, so 4 in the x and 3 in the y, and then putting that as a unit vector, that's 4/5. The length of 4 and 3 is 5, so 4/5 I and 3/5 j, so that's the unit vector of the AC axis. We dot product that with our moment vector, which was 15i, 4j, and 36k. So 4/5 of 15 plus 3/5 of 4 gives us 2.4. 4/5 of 15 is 12. 3/5 of 4 is 2.4. So our magnitude of the moment of this force about AC is 14.4. And putting that as a Cartesian moment vector, we'd have 4/5, back again, 4/5 times the 14.4 would give us 11.52 in the x-axis. And then 3/5 of 14.4 is 8.46. So that is our Cartesian moment vector about AC is 14.4. The square root of the sum of the squares is 14.4. To check that in SolidWorks, or a 3D CAD system, we would first have to create a plane that's perpendicular to AC. And I've created one there. Let me just show you how I did that. I say insert a reference plane that's pick that axis and then pick its endpoint here. And that would place a plane perpendicular to AC. And the only force that's creating a moment about this is the force that would lie in that plane. Anything else that's parallel to that axis would be just putting a tension on it. Anything parallel to it would be either tension or compression. In this case, it would be tension because it would be pulling on it. So we'd first have to get the angle there. So if we measure turn that plane on there. If we measure the angle, we say, what is the angle between my force vector and that plane? It's 53.13 degrees. So the cosine of that angle, 53.13, times 13 would be the force that's creating a moment, and then the perpendicular distance from that line to this line. In other words, those are skew lines. They are non-intersecting, non-parallel lines. And if we see what's the perpendicular distance from there to there, that just gives us a straight line distance. Let's actually draw a line in there. We'll say insert a 3D sketch, and let's go from AC down here to our force vector, and we'll tell the system the line there and our force vector, let's make that perpendicular. And let's make from this line up to AC, we'll make that one perpendicular. So there's our common perpendicular. And so the cosine of the 53 angle times 13 times this distance, and that distance there is 1.846. So the cosine of 53.13 times our force of 13 pounds times the 1.846 gives us 14.4, and that's exactly what we got using our manual method, using the dot product. So this might be a little bit more intuitive to understand, to validate the dot product of the moment vector. Hopefully that is helpful in you trying to solve this problem and validate it using the CAD system. Thank you very much for listening.